A recent development in valve replacement technology has been the development of transcatheter aorta valve implantation technology. The valve is inserted in the aorta or pulmonary valve position via a catheter-based technique avoiding open heart surgery. The Robert W.M. Freiter Cardiovascular Research Center at the University of the Free State developed the bovine pericardial tissue that is used to produce the TAVI valve in collaboration with the University of Stellenbosch.
My interest in TAVI started it's more than 10 years ago, and it was a very exciting new field, and I wanted to get into it. There were a few problems. One of them were that the current designs were extremely expensive and were not focused on younger people like we tend to treat here in South Africa. And so I set out with a team of engineers and we designed a valve, and we were very excited to start testing it in animals. But the tissue I had access to did not perform very well in the animal implants. And we tried many different techniques and things, and in the end I realized it's not going to work. Although I was despondent for a bit, I remembered that we do have an expert in the field in the country, and so I contacted Francis Smith in Bloem, and his team's got years and years of experience with a variety of tissues, and we got together. Both of us were excited because we can both add something interesting to the project, and from there on it's been a very exciting ride, and we've made huge progress, and I'm very excited to work with him and his team at the Freiter Institute, because it's things are just happening, things are progressing, and it's going very well. So I'm very excited about the prospects of our new valve and what we could potentially do.
In several surgical disciplines, artificial and biological materials are needed as potential substitution materials for reconstructive surgical procedures, including suitable biomaterials that can be used to repair and replace various soft tissues such as tendons, skin, vascular grafts, and heart valves. These biomaterials need to be both versatile and compatible with human tissues. Unfortunately, there is still no ideal tissue with long-term applications, especially for pediatric cardiac patients where immune reactions and calcification remains a big problem. Our department has been developing alternative processing techniques for homografts, that's tissue from human origin, or xenografts, that's from animal origin, for example, bovine pericardium, for decades. To reduce early tissue degeneration and calcification as a result of immune processes, a patented multi-enzymatic decellularization technique has been developed by the Freiter Center. Synergy between the detergents was shown, providing an advantage in strength while limiting damage to the remaining scaffold. This technique has been applied to both xenografts and homografts, where extensive decellularization has been shown in large animal models. The decellularized homografts have the potential to be a unique product for pediatric patients requiring right ventricle outflow tract reconstruction, while xenografts offer the opportunity of an unlimited supply of tissue where donor shortages remain an issue for homograft use. Also, a unique processing technique for fixed and unfixed decellularized tissue has been developed. This tissue will be used in the TAVI valve construction and tested and compared to 2 commercial tissues in a large animal study.
Professor Hannes Meyer and Prof. Leon Neethling started the homograft heart valve bank in the Free State in 1984, and I joined them soon after. Up to date, 3 PhDs have been done on homografts, and it was proven that the harvesting time from deceased donors could safely be prolonged to enlarge the donor pool. In the first 2 PhDs, Dr. Dreyer Bester and Prof. Francis Smith demonstrated that the cryopreservation process, combined with the extended harvesting time, effectively produced non-vital valves that demonstrated excellent resistance to calcification in sheep. And the logical next step was to develop decellularized homografts. So in my PhD research on decellularized pulmonary homografts, we could demonstrate excellent recellularization and mitigation of calcification in the juvenile sheep model. At the same time, a glutaraldehyde fixed bovine pericardial patch was produced. However, in my master's study in 2007, the glutaraldehyde fixed bovine patch demonstrated severe calcification when compared to a commercial tissue and tissue processed with an alternative biochemical processing method, and the clinical use was terminated. Based on this experience in both the homograft and the bovine pericardial patch fields, a tissue engineering project was initiated under the guidance of Prof. Francis Smit and Prof. Pascal Domen from the Cardiac Surgery Department at the University of Rostock in Germany, focusing on the development of a novel decellularization and sterilization process. And this technology was recently patented as a patent in the United States.
Dr. Liana Leiker demonstrated synergism between the decellularization agents used in the patented decellularization method. In combination, these decellularization agents caused less damage to the collagen scaffold with excellent retention of both strength and structure. In my PhD, bovine pericardium processed with patented decellularization method was compared to a commercial patch and a decellularized, fixed and detoxified scaffold, which was decellularized according to our patented method and fixed and detoxified in the same manner as the commercial patch. These patches were implanted in a large animal model. All three pericardial groups demonstrated excellent clinical, structural and morphological results. The pre-implantation commercial patch demonstrated collapsed, dense collagen not favorable for cellular infiltration. However, the collagen of the decellularized, fixed and decellularized scaffold was wave-like with adequate pore size to promote cellular infiltration. Importantly, excellent host cell infiltration was observed in the explanted decellularized pericardium. This may be a living patch, at least in the sheep model.
In Dr. Burtis' PhD, a fibrous encapsulation was observed at explantation of the glutaldehyde fixed decellularized bovine pericardium. This was also observed for two commercially glutaldehyde fixed bovine pericardium products. The formation of this fibrous encapsulation is especially of concern when using the tissue for heart valve development, as it might influence the thickness of the tissue and therefore valve function. A new processing technique for fixed and non-fixed decellularized bovine pericardium has been developed at the Freitas Center. The aim is to prevent the formation of the fibrous encapsulation or allow us to use unfixed, decellularized tissue for valve manufacturing. This tissue will be used in the TAVI valve design.
The study will evaluate the efficacy of unfixed, decellularized bovine pericardium in a TAVI configuration. In order to verify its competence, the valves are submitted to in vitro hydrodynamic and durability testing. Hydrodynamic performance is assessed through parameters such as the effective opening area, transvalvular pressure drop, and closing volumes, which must meet the minimum requirements as per ISO specification. These metrics are obtained through pulsatile flow testing in a cardiac pulse duplicator, mimicking typical left heart conditions. Durability is assessed in an accelerated wear tester, which submits the valve to continuous opening and closing cycles at an elevated frequency. Hydrodynamic performance is continually assessed throughout the durability testing phase up to a minimum of 200 million cycles. After confirming proper valve function, the next step is to implant it into a large animal model to evaluate calcification, tissue remodeling, and the mechanical integrity of the tissue. As part of my Masters in Engineering, I am exploring alternative valve frame designs with possible durability and manufacturing cost advantages utilizing the same tissue.
We hope to demonstrate superior results specifically focused on the use of this tissue valve in younger patients. This will make an important and cost-effective contribution in the management of younger patients with rheumatic heart disease and congenital lesions of the right ventricle outflow tract.